Hello everyone. In this real analysis video, we're going to be proving this early theorem about convergent sequences. And it is that every convergent sequence is bounded. It's just a useful thing to note in a lot of cases. So first of all, right, let's say what we mean by this, right, is if I have some sequence an, which is, let's say, 1 over n, we know, for all n in n, we know that an converges to 0, right? And, well, notably, this sequence is bounded, right? And so what bounded means is that there is some, largest absolute value of the, terms in the sequence. Now, that's not a proof. I'm just, showing an example of maybe verifying where it would come up. Should note here the definition of boundedness, right? So definition. So a sequence an in R is bounded if, well, if what? If there exists some m greater than 0 such that the absolute value of an is strictly less than m for all n in n. Okay, and so all that really is saying is that we can find some upper bound on the absolute values for all terms. Okay, so every convergent sequence is bounded. So that means convergence implies boundedness. Boundedness does not necessarily imply convergence, right? So we can look at the, we can of course look at an example like bn, which is -1 to the n, right? So the absolute value of bn is equal to 1, which certainly is less than, I don't know, 2, right? Maybe choose that for m. But the sequence does not converge, right? It oscillates between -1 and 1. It has two convergent subsequences, 1 and -1, the repeated ones and the repeated -1, so it itself does not converge. Okay, well, let's look at the proof of this. So the proof of this is not that hard, right? So the logic here is that if I take the real number line and I take any sequence in it that converges, so let's say my sequence will converge to this A here. And I have some sequence, and maybe it's, I don't know, it's doing something, it's meandering. But I know that at some point it will be and stay within a radius, let's say 1, a minus 1, a plus 1, right? It will stay within a radius of 1. And this is part of the definition of convergence, right? Okay, so let's maybe look in more details. And so, sorry, I guess I should finish my sentence. If it stays within this radius, then we know that at least, after the point it enters, let's say some n naught, it enters. Once it reaches n equals n naught, it enters this radius and it never leaves. So we know it's definitely bounded after that. And before, well, it's only finitely many terms, right? So we just take whatever the largest one of all those are. Okay, so let's actually do the proof here. So suppose an is a sequence of real numbers such that an converges to a. So we know that for all epsilon greater than 0, there exists an n equal, well, there exists an n, maybe I'll call it n epsilon, right, based on that epsilon in n, such that if n is greater than or equal to that n epsilon, this tells us that an minus a is less than epsilon. This is true for all epsilon. So let's just take epsilon equal to 1, right? Take, if I can spell take epsilon equal to 1. That means that we know there exists some n1, right? n1 in n, such that for all n greater than or equal to n1, such that n being greater than or equal to n1 implies that an minus a is less than epsilon. So we know it converges to this real number, right? And so we know that if we think of all our terms in the sequence, a1, a2, dot, 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 a n1 minus 1, a n1, a n1 plus 1, dot, 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 we know that all of these terms in the sequence, right, will be less than, definitely less than, a plus 1. Right, maybe the absolute value of a plus 1. And I should be clear, maybe the absolute value of an is definitely less than. Because we're saying that the distance, right? Well, I guess I should put a 1 there, right? My mistake. So let me repeat the sentence here, right? So we took epsilon equal to 1. There exists an n1 in n such that n being greater than n1 implies the distance an is from a is strictly less than 1. It wasn't really wrong before because epsilon is 1, but that's more what I mean, right? I mean, we picked epsilon to be 1. So we know that all of these terms after that n1 are, well, they're going to be at most, not at most, but less than 1 away from a. So sure, they're strictly less than the absolute value of a plus 1. And now we just have these finitely many terms, right? Finitely many terms here that could be bigger, right? In the sequence here, right? For example, that guy was bigger. But, well, we can just, so this is not an upper bound for the entire sequence, but, right, if we think about what's the largest out of all these, right? So if we let m equal the max out of absolute value of a1, absolute value of a2, dot, 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 absolute value of a n1 minus 1, and this value, absolute value of a plus 1, then certainly the absolute value of an is less than or equal to m for all n in n, right? It's certainly less than all these values, and then we know after this a n1 point, it's always less than this value. And so there we go. Since it's convergent, we can take this maximum because there's finitely many points before it reaches this distance of 1 from where it converges to, and otherwise we're done.